Hello everyone, this is Aishwarya from Sri Venkateshwara College of Engineering. Today in this video you will be knowing about the problems that computers cannot solve, the Turing machines. Defining computability. Computability refers to the ability of a problem to be solved by an algorithm or a computational model. Turing machines are used to formalize the notation of what it means for a function to be computable. A problem is considered computable if there exists a Turing machine that consists of a finite amount of time. The halting problem asks whether a given Turing machine will eventually halt when run on a specific input or continue running forever. Alan Turing proved in 1936 that no general algorithm can solve this problem for all the possible Turing machine and inputs. Implications of the halting problem. The halting problem illustrates intrinsic limitations in algorithmic computer. It implies that there are clear boundaries on what can be computed by machines. Understanding this limitation is crucial for computer scientists and mathematicians. Computable problems. Beyond the halting problem, there are many other problems that cannot be solved by Turing machines. Examples include the problem of determining whether two Turing machines produce the same output for all inputs. These non-computable problems highlight the complexity of certain computational challenges. The Einstein problem, proposed by David Hilbert, the Einstein problem asks if there is a general algorithm that can decide the truth or falsehood of any statement in first-order logic. Turing and Alonzo Church independently showed that no such algorithm exists. Rice theorem. Rice theorem states that any non-trivial property of the language recognized by a Turing machine is undecidable. This means you cannot decide, for example, whether a Turing machine accepts all strings or no strings. The theorem highlights the richness of the set of languages recognized by these machines. Problem of undecidable languages. Some languages are undecidable, meaning there is no Turing machine that can determine membership for all possible strings. An example of such a language is the set of all Turing machines that halt on a blank type. These undecidable languages illustrate the limits of formal systems and algorithms. Complexity classes. Complexity classes categorize problems based on their solvability and resource requirements. Problems that cannot be solved by Turing machines fall outside these classes. Understanding complexity helps to identify computationally difficult or impossible problems. Limitations of algorithmic solutions. Not all problems can be solved through algorithmic means, even if they are well defined. Some problems require human intuition or creativity that machines cannot replicate. This distinction is important for understanding the role of computers in problem solving. Inherent limitations of computation. Inherent limitations exist when the realm of computation, as shown by the work of Turing. These limitations suggest that some problems are fundamentally beyond the reach of mechanical computation. Recognizing these limitations helps to set realistic expectations for computational capabilities. Gödel's incompleteness theorems. Gödel's incompleteness theorem complement the findings of Turing machine regarding computability. They show that in any sufficiently powerful formal system, there are true statements that cannot be proven. This aligns with the notation that not all mathematical problems can be resolved algorithmically. Practical implications of non-computability. Non-computable problems have real-world implications in fields such as computer science and mathematics. They influence how researchers approach problem solving in complex systems. Awareness of these limitations can guide the development of more effective algorithms. The role of approximation. For some non-computable problems, approximation methods may provide useful solutions. While exact answers may be unattainable, approximations can yield valuable insights. This approach is particularly useful in fields like optimization, and artificial intelligence. Completeness. A system is Turing complete if it can simulate a Turing machine and perform any computation. Many programming languages are Turing complete, allowing for complex algorithmic solution. However, Turing completeness does not imply that all problems can be solved within those systems. Future of non-computability. As technology evolves, new approaches to computation may emerge, but certain problems will remain unsolvable. Quantum computing and other advanced methods are being explored for complex problem solving. Nonetheless, the fundamental limits established by Turing and others will likely still apply. Philosophical consideration. The existence of non-computable problems raises philosophical questions about the nature of knowledge and understanding. What does it mean for something to be knowable in an algorithmic sense? This question challenges our perception of intelligence and computation. Characteristics of problems Turing machines cannot solve. Undecidability, incompleteness, non-computability. Undecidability, these problems lack a universal algorithmic solution. Incompleteness, some problems fall under Gödel's incompleteness theorem, where certain truths cannot be proven with a formal system. Non-computability, they require more than algorithmic step, potentially infinite or non-mechanical reasoning. These limitations highlight that while Turing machines are powerful models of computation, there are fundamental boundaries to what they can compute. Conclusion. Embracing limitation. Recognizing the limitation of computers is as important as understanding their capabilities. The study of unsolvable problems provides insights that can lead to better computational practices. Embracing these limitations encourages innovation and creativity in problem solving approaches. Thank you.